School, Erlang Term Storage, ETS. Erlang Term Storage, commonly referred to as ETS, is a powerful storage engine built into OTP and available to use in Elixir. In this lesson, we'll look at how to interface with ETS and how it can be employed in our applications. Overview. ETS is a robust in-memory store for Elixir and Erlang objects that comes included. ETS is capable of storing large amounts of data and offers constant time data access. Tables in ETS are created and owned by individual processes. When an owner process terminates, its tables are destroyed. By default, ETS is limited to 1,400 tables per node. Creating tables. Tables are created with new_to, which accepts a table name and a set of options, and returns a table identifier that we can use in subsequent operations. For our example, we'll create a table to store and look up users by their nickname. So we have table equals Erlang ETS new user lookup set protected, so options. Much like gen servers, there is a way to access ETS tables by name rather than identifier. To do this, we need to include the named table option. Then we can access our table directly by name. So Erlang ETS new user lookup, and then we add named table. Table types. There are 4 types of tables available in ETS. Set. This is the default table type. 1 value per key. Keys are unique. Ordered set. Similar to set, but ordered by Erlang/Elixir term. It is important to note that key comparison is different within ordered set. Keys need not match so long as they compare equally, i.e. 1 and 1.0 are considered equal. Third type, bag. Many objects per key, but only one instance of each object per key. Duplicate bag. Many objects per key, with duplicates allowed. Access control. Access controls. In ETS, access control in ETS is similar to access control within modules. We have public, read-write available to all processes. We have protected, read available to all processes, only writable by owner process. This is the default. Private. Read and write limited to owner process. Race conditions. If more than one process can write to a table, whether via public access or by messages to the owning process, race conditions are possible. For example, 2 processes each read a counter value of 0, increment it, and write 1. The end result reflects only a single increment. For counters specifically, Erlang ETS update counter 3 provides for atomic update and read. For other cases, it may be necessary for the owner process to perform custom atomic operations in response to messages, such as add this value to the list at key results. Inserting data. ETS has no schema. The only limitation is that data must be stored as a tuple whose first element is the key. To add new data, we can use insert_to. So ETS insert user lookup, and then the key that we want to insert at, and then the rest. New, Sean, Elixir, Ruby, Java. If we try to insert When we use insert2 with a set or ordered set, existing data will be replaced. To avoid this, there is insert new to, which returns false for existing keys. So it returns false since we already inserted with key doomspork. Data retrieval. ETS offers us a few convenient and flexible ways to retrieve our stored data. We'll look at how to retrieve data by key and through different forms of pattern matching. The most efficient and ideal retrieval method is key lookup. While useful, matching iterates through the table and should be used sparingly, especially for very large data sets. Key lookup. Given a key, we can use lookup2 to retrieve all records with that key. ETS lookup user and then the key, and it returns the tuple. Simple matches. ETS was built for Erlang, so be warned that match variables may feel a little clunky. To specify a variable in our match, we use the atoms $1, $2, $3, and so on. The variable number reflects the result position and not the match position. For values, result position and not the match position. For values we're not interested in, we use the underscore variable. Values can be used in matching, but only variables will be returned as part of our result. Let's put it all together and see how it works. So match this is what we want to return. Look at this. This is the key here. This is the rest. Let's look at another example of how variables influence the resulting list order. 99, 1. What if we want our original object, not a list? I'm not sure. What if we want our original object, not a list? We can use match object to, which regardless of variables, returns our entire object. Match object. Advanced lookup. We learned about simple match cases, but what if we want something more akin to a SQL query? Thankfully, there is a more robust syntax available to us. To look up our data with select2, we need to construct a list of tuples with arity 3. These tuples represent our pattern, 0 or more guards, and a return value format. Our match variables and two new variables, $$ and $_ can be used to construct the return value. These new variables are shortcuts for the result format. $$ gets results as lists, and $_ gets the original data objects. Let's take one of our previous match2 examples and turn it into a select2. Although select2 allows for finer control over what and how we retrieve records, the syntax is quite unfriendly and will only become more so. To handle this, the ETS module includes fun2ms1, which turns the functions into match specs. With fun2ms1, we can create queries using a familiar function syntax. Let's use it and select2 to find all usernames with more than 2 languages. ETS fun2ms We pass in a function. This is kind of the matchery. And then we have a guard. When length of links is greater than 2, return the username. Alright, this is starting to become readable. Want to learn more about the match specification? Check out the official Erlang documentation for match spec. Maybe later. Deleting data. Removing records. Deleting terms is as straightforward as insert to and lookup to. With delete to, we only need our table and the key. This deletes both the key and its values. We have ETS, delete, and then we give it the table name and the key here, deemspork. Removing tables. ETS tables are not garbage collected unless the parent is terminated. Sometimes it may be necessary to delete an entire table without terminating the owner process. For this, we can use delete one. Example ETS usage. Given what we've learned above, let's put everything together and build a simple cache for expensive operations. We'll implement a get_for function to take a module, function, arguments, and options. For now, the only option we'll worry about is TTL. For this example, we're assuming the ETS table has been created as part of another process, such as a supervisor. So we have this simple cache module that has a get and a lookup, and a check freshness, and cache apply, which respectively do retrieve a cached value or apply the given function caching and return the result. Look up a cached result and check the freshness. Compare the result expiration against the current system time. And apply the function calculate expiration, cache the result. To demonstrate the cache, we'll use a function that returns the system time and a TTL of 10 seconds. As you'll see in the example below, we get the cached result until the value has expired. ETS new simple cache, name table, simple cache. Make a test. Get test. No arguments sent to that. Total of 10. Convenient. After 10 seconds, we try again. We should see a fresh result. As you can see, we are able to implement a scalable and fast cache without any external dependencies, and this is only one of the many uses for ETS. Disk-based ETS. We now know ETS is for in-memory term storage, but what if we need disk-based storage? For that, we have disk-based term storage, or DETS for short. The ETS and DETS APIs are interchangeable with the exception of how tables are created. DETS relies on OpenFile2 and doesn't require the named table option. If you exit IEX and look at your local directory, you'll see a new file, disk storage. One last thing to note is that DETS does not support ordered set. Like ETS, only set, bag, and duplicate bag. Be right back.